Hi everyone, this is an example of a gas stoichiometry problem. We're going to follow our same 4 steps. We must pay extra attention to our interpretation of the question to help us choose wisely in step 2 and step 4. Here we go. The conversion of sulfur dioxide and oxygen gases to sulfur trioxide gas occurs at 100 degrees Celsius and 200 kilopascals. If 800 grams of oxygen are consumed by the reaction, what volume of product forms? We need to take our time to come up with the balanced chemical reaction. Here, the key words are and to. We're going to convert sulfur dioxide and oxygen. Sulfur dioxide and oxygen are going to get converted to sulfur trioxide. Let's get that down. Sulfur dioxide, SO2, the molecular compound with the prefix in there, and oxygen, O2. Oxygen gas is diatomic. It's going to produce sulfur trioxide, SO3. This is a particular kind of reaction. It does not match one of our 5 normal reactions. We might trick ourselves into thinking it's some kind of single replacement or something like that. However, sulfur dioxide and oxygen are molecular compounds. And so it doesn't fit one of our established kinds of reactions, which is why all of the chemicals involved are listed in the question itself. It's a little bit tricky to balance because we have oxygen in 2 places on the left-hand side, but only 1 place on the right-hand side. What I need to do is balance it like that. When I look at this now, here there's 2 sulfurs, here's 2 sulfurs. In total, on the left-hand side, this right here is 4 oxygens, and here's 2 more. So in total, on the left-hand side, there are 6 oxygens, and over here, 2 times 3, 6 oxygens. So not only do I have some real choices to make in terms of the math, the reaction itself here was a little bit tricky, and so was the balancing. Moving on. This whole thing takes place at 100 degrees Celsius and 200 kilopascals. Because the question ultimately asks, what volume of product forms? We only have the one product, sulfur trioxide. What volume of product forms? This is the V, which we don't know. It's a gas. This whole thing happens at 100 degrees Celsius and 200 kilopascals. We could apply that temperature and pressure to any of the 3 chemicals. But here's the unknown part of the question. And so the temperature goes there, 100 degrees Celsius, and the pressure, 200 kilopascals. I'm already thinking that, every time in the whole course, the temperature has to get converted into Kelvin. That's a thing to think about. Here we have, that's where the question mark is. It's also R. We have also 800 grams of oxygen being consumed. Here's the oxygen, 800 grams, that's the mass. The mass of the oxygen is 800 grams. Yes, the oxygen is also at 100 degrees Celsius and 200 kilopascals, and so is the sulfur dioxide. However, looking ahead to the work that we're going to do, this question sets up this way. And because those 800 grams, we know them, they are given. Now we need to make a choice. Which formula are we going to use to convert into moles? P times V over RT. We might feel tempted, but we clearly don't have the volume. We don't have a volume to use Avogadro's law. We don't have a volume to turn it into some kind of solution stoichiometry problem. We do have a mass. We can do mass over molar mass. We have our 800 grams of oxygen over the molar mass of O2, 32. Find moles. Our next step, multiply by R over G. R over G. This whole thing represents what we've been calling red N. To solve for the volume, I'm making a choice. There's three possible ways to solve for volume here. We could divide by concentration. We don't have a concentration. We can multiply by the molar volume. This question doesn't mention STP or SATP, so we must be using the ideal gas law. This whole thing is red N. The volume is going to be red N times R times T over P. So our last step here is times R times T over P. This is multiplied by R. That's the ideal gas constant, 8.314 kilopascal liters per mole Kelvin. There's the red N times R. Now we're going to multiply by T in Kelvin. The temperature is 100 degrees Celsius. We're going to add 273.15. That's 100 plus 273.15 Kelvin. If you just want to write in 373.15 there, that does the trick. This is over the pressure 200 kilopascals. 200 kilopascals. Quite an operation to set all of that up. And now there's so many buttons to push. We have 800 grams divided by the molar mass, 32, times 2 over 1, times 8.314, times, turns out to be 373.15. This is divided by 200. We get 775.592275. With our three significant digits from the question, 100, 200, 800, equals 776. And this was the volume that we were solving for, liters. When we have a gas stoichiometry question, it's likely that we're going to see the word gas show up a bunch of times. We need to be really careful with our interpretation so that we can choose the correct path to navigate through these 4 steps. There's lots of different variations. We might have a question like this one where we started from mass and ended up using R over G and the ideal gas law to solve for the volume. We need to be especially careful when a question does ask for the volume because we have 3 options down here in our 4th step. We must choose the correct one. And I hope that helps.